Detailed balance, also known as reversibility, is a property possessed by certain Markov chains, and it's used in Markov chain Monte Carlo very frequently to construct a Markov chain with the desired stationary distribution. So the definition is very simple, so we'll just start off with the definition. A PMF pi on some set of states script x satisfies detailed balance with respect to a transition matrix T satisfies if we have the following property. If pi a TAB equals pi b TBA for any pair of states A and B. So it's this sort of symmetry property here. And a couple remarks about this. The first thing to note, first remark, is that if pi satisfies detailed balance with respect to T, then in fact pi is a stationary distribution for any Markov chain with transition matrix T. So detailed balance implies stationary dist, and this is the useful fact for Markov chain Monte Carlo, and let's verify this. So in order to check that pi is a stationary distribution, we need to have pi t equal to pi, or in other words, the sum over b of, let's make it the sum over a of pi a TAB. We have to have that equal to pi b. That's what this equation is saying, for all b. So let's see if that holds. So we have detailed balance, and so we can use this equation. So let's use that equation. Let's plug it in here. So we get pi b TBA. And now, what do we have? Pi b is a constant, so we can pull that out. Sum over b TBA. And this is that since the rows of any transition matrix are they sum to 1, because any transition matrix is a stochastic matrix. Then if we, this is a sum over A, of course. Summing over A is summing over the bth row, the row B of this transition matrix. So this is just pi b. So therefore, and of course this holds for any b, so therefore this is a stationary distribution. A second remark is to explain what reversibility is. So detailed balance is equivalent to reversibility. They're just two different names for basically the same thing. Usually people say that a Markov chain is reversible, and they say that a PMF and transition matrix satisfy detailed balance. So it's just a little bit, just a terminology. So a Markov chain is reversible if it has a stationary distribution pi which satisfies detailed balance with respect to its transition matrix. So it's reversible if this can be satisfied for its transition matrix. And you might be wondering, why, what is this reversibility? Why is it called reversibility? So I just wanted to explain that terminology. The reason why it's called reversibility, at least the best reason I can think of, is that if you have a Markov chain x0 up to xn, and I'll use this sort of shorthand to denote that this is a Markov chain with initial distribution pi and transition matrix T, and not only is pi the initial distribution, but pi is also a stationary distribution, which actually is implied by, we could just assume what our next assumption was going to be that pi satisfies detailed balance with respect to t, and that of course implies that pi t equals pi, as we just saw. So if we have these properties, then in fact this implies that xn minus 1 down to x0 is also a Markov chain with the same initial distribution and the same transition matrix. So it's reversible in some sense. If you flip it from front to back, then it has the same distribution. And this is the case as long as detailed balance is satisfied. And note here, I didn't write it explicitly. I mean, it's in the notation here, but another requirement for this equivalence, for this to imply this, is that pi is also the initial distribution for this Markov chain. Okay, so that's detailed balance and reversibility, and I'd like to give you a little intuition for what this is saying, because detailed balance has a very, very natural, intuitive interpretation. And so I'd like to just explain this intuition. And the intuition is this. So this is the sort of expression that we want to understand. Pi a tab equals pi b tba. And the interpretation is the following. We interpret this product as the mass, the quote-unquote mass, moving from A to B, and we interpret this side as the mass moving from B to A. So in other words, we envision, this is all just sort of heuristic, just sort of intuition, but we envision that, you know, all these states, maybe these are the different states of the system in our set X, and there's a certain amount of probability mass at each of these, maybe something like this, and the amount at each of these is determined by pi. So if this was A here, then the height of this column, I'm sort of drawing a column here, the height of this column would be pi A, and the height of this column would be pi B. And this mass moving from A to B is, so the TAB is the fraction of A, if we were to imagine sort of running the system at one step forward in time. TAB is the fraction of the mass at A that gets shipped to B. So this goes to B, and TBA is the fraction of the mass at B that gets shipped to A in that sort of one time step. And even though those fractions may be different, what this equality is saying is that the amount of mass that is being exchanged between A and B is the same. The amount going from A to B equals the amount going from B to A. And if this holds for all pairs, then that's equivalent. You know, the mass moving between any two pairs is the same. So maybe to make that a little more concrete, sort of a real-world analogy, since usually, you know, most people don't think much about moving probability mass around, let's put it in terms of dollars and cents. So let's say we have a little economy. So let's envision a little economy, and there's, let's say, 3 people in our little economy. We have, let's say, Anne, we have Bob, and we have Chuck. Anne, Bob, and Chuck. And so we're going to envision that the total amount of money, so there's only 3 people in our little world, and the total amount of money, you know, that exists in this world is $1. And this is divided up between Ann, Bob, and Chuck in the following way. So Ann, pi A will be the amount of money that Ann has. So this is the money held by Ann, A for Ann. Pi B will be the money held by Bob, and of course pi C is the money held by Chuck. And thinking back to the interpretation as a probability distribution, these numbers sum to 1 in a probability distribution, and here they sum to $1. So this is the sort of the fraction of $1 that Ann has. And now the interpretation of this quantity, let's use a different color, pi A T A B, in this sort of analogy, is that, so Ann has pi A money, and Ann is going to give Bob TAB fraction of her money. So TAB is some number between 0 and 1. It's some transition probability. And Ann is going to give that fraction of her money to Bob. So Ann is going to give this amount of money to Bob. So this is the amount of money given, or amount of money from Ann to Bob. And so we're imagining sort of one day in the life of these three people. One day in the life of this little economy. In this one day, Ann gives this amount of money to Bob, and likewise, the same interpretation is that pi B, TBA, is the amount of money that Bob gives to Ann. Pi B is the amount of money that Bob has, and TBA is the fraction of Bob's money that he gives to Ann. So this is the money from Bob to Ann. And when these are equal, when this equality is satisfied, when these are equal, then they give the same amount of money to each other. Ann gives the same amount to Bob as Bob gives to Ann. So there's sort of a balance here, a sort of balance between the two of them. And when this equality holds for all pairs A and B, then between any two people, the amount of money that exchanges hands balances out. So the amount of money that Bob gives to Chuck equals the amount of money that Chuck gives to Bob, and same for Ann and Chuck. And so it's fairly obvious that after that day, each of them will have the same amount of money that they started out with. So Ann will still have pi A money, pi A dollars. And that observation, which is intuitively obvious when you think about it this way, using this sort of analogy, that observation is just the observation that pi is a stationary distribution. If it satisfies detailed balance for t, then it's a stationary distribution. That's exactly what this is saying. So in order to go, to bring this back from analogy world, from sort of economy dollars and cents world back to probabilities, all you have to do is replace dollars by probability mass. And so that's the sort of intuition here for the mass moving between these different things, is that it's, you can think about it in this sort of way. You could replace dollars by any other quantity. You could even make a physical analogy or something like that. Imagine, some quantities of goods moving around or something like that. Okay, so I hope that was a useful intuition for you. I think it's nice way to sort of envision what detailed balance really means. So of course, so that explains the name, right? That explains, it's because they're balanced between them, and it's sort of detailed balance. It's detailed in that between any pair, they are balanced.